Check. Good morning, students. Welcome to the lecture 14 revision class of Design of Machine Members 1 for mechanical second year, second semester students. Today we are discussing the Unit 2 concepts for your revision classes. So we will discuss this class in brief for the exam point of view. Okay, right, we'll start the class. Coming to the contents of the syllabus, coming to the content of the unit 2, in the unit 1 what we have discussed is the introduction about the machine elements, the design considerations of machine design, selection of manufacturing processes, and various engineering materials like metals and non-metals. Coming to the metals, we have alloy metals and non-ferrous metals and non-ferrous metals. Coming to the non-metals, we are having glass, rubber, epoxy, composites, etc. Right? So for any metal or non-metal, we have to do some sort of analysis. Why? Because we are using these materials for some applications, right? For that reason, we are having various types of properties of materials as well as the stress relations. So in the unit 1, we have discussed about the introduction of various types of properties as well as stress analysis. In the unit 2, we will discuss about the stress concentration factor, theoretical stress concentration factor, fatigue stress concentration factor, notch sensitivity, design for fluctuating stresses, endurance limit, estimation of endurance strength by using Goodman's life, Soderberg line, and modified Goodman's line. So these are the current topics what you are having in the unit 2 of design of machine members 1. Okay, right. So if you see the stress concentration concept, so whenever a machine component changes the shape of its cross section, right? So whenever the object is with so and so diameter, right? So whenever it is changing the shape of the cross section, so if you see the cross section up to here, you are having one diameter. When you see the cross section cutting at this point, you can see cross section is reduced, right? The simple stress distribution no longer holds good, and neighborhood of the discontinuity is totally different. His irregularity in the stress distribution caused by the abrupt changes of a form is called stress concentration. Got it? So whenever there is abrupt changes in the cross section of any solid part, right? The irregularity of stress distribution, these drastical changes formed is known as stress concentration. It occurs for all kind of stresses in the presence of fillets, notches, holes, keys, splines, surface roughness, and scratches, etc. Right? So, so for example, if you want to consider a member of different cross section under a tensile load by showing the figure, a little consideration will show that nominal stress in the right and the left hand sides will be uniform, but in the region where the cross section is changing, a redistribution of the force within a member must take place. Material near the edges is stressed considerably higher than the average value, right? So if you take the cross section of any rod, right? So this is one this is one diameter rod, right? So whenever the cross section is reduced to some thickness, right? This is a thickness. So the diameter is reduced from d to small d. Let us think by taking the tensile forces, by taking the tensile forces on both sides. The maximum stress occurs at the some point on the fillet is directed parallel to the boundary at the point. Okay. Next, theoretical or form stress concentration factor. The theoretical or form stress concentration factor is defined as the ratio of the maximum stress of the member to the nominal stress of the same member based upon the net area. So therefore, the stress concentration factor Kt is equals to maximum stress by nominal stress. Maximum stress by nominal stress. Next, in cyclic loading, the stress concentration in ductile materials is always serious. In cyclic loading, the stress concentration in ductile materials are always big serious because the ductility of material is not effective in relieving the concentration of the stress caused by what? The defects like cracks, flaws, any surface roughness, discontinuity, etc. If the stress at any point in a member is above the endurance limit, a crack may be developed under the action repeated load, and the crack will lead to the failure of the member. Got it? Next, stress concentration due to the notches and the holes. Consider a plate with transverse elliptical holes subject to a tensile load. We see from the stress distribution that the stress at a point away from the hole is practically uniform and the maximum stress will be induced at the edge of the hole. Therefore, the maximum stress sigma maximum is equals to sigma of 1 plus 2a by b, and the theoretical stress concentration factor At is equals to sigma max by sigma 1 plus 2a by r. So if you see the various stress concentration at different holes, so here sigma max is 5 delta, 5 sigma, 2 sigma, 3 sigma. So a by b is 2, half and 1. So see the changes in the concentration. So here the area A, right? So the elongation, whenever the pressure is forces are applied in this direction, so the elongation takes place at this point sigma max. Okay, so this is nothing but the stress concentration due to the holes. Next, the stress concentration at a notch tension member is influenced by the depth of the notch and the maximum stress which applies to the member having the notches that are small in comparison is obtained by the following equation. Sigma max is equals to sigma of 1 plus 2a by r. Okay, that is equals to the distance a, center r, for the notches point of view. This is a formula. Next, how to reduce the stress concentration concept. What are the various methods of stress concentration, right? So whenever there is a change in the cross section, okay, it may be the square, or it may be the circular, or it may be any other shape. Whenever there is a change in the cross section, such as shoulders, holes, notches, keyways, etc., etc., and where is an interface fit between a hub or a bearing race and the shaft, then stress concentration results, right? So a device or a concept that is useful in assigning a design engineer to see the mitigated is that the stress flow. If you see the mitigation of stress concentration means the stress flow lines shall maintain the spacing for as possible. So if you see the various methods, see here the stress concentration factor is very poor, very poor. So the sharp edges. Okay. Next, second one, it is good. So this one is in this way. Okay. So whenever the cross section is having some sort of edges, so whenever the edges are very smooth line, whenever there is cross section it is preferred, and also this type of small integrations and the cross sections is also preferred. So these are the various ways of reducing the stress concentration factor. Got it? Next, if you see the figure, the stress reducing concentration is cylindrical members with shoulders. So if you see the stress lines tend to bunch up and cut very close to the sharp re-entrant corner. In order to improve the situation, the fillets may be provided and the give more equally spaced flow lines. Okay, so see here, it is a pour. So the momentum M is a pour. So whenever you are having the small integration, it is good. It is also preferred. Next. So if you see here, the pressure, the tensile forces is acting in this direction. So here the point is very poor point. So whenever it is there, it is you are having a preferred concepts. Next, reducing the stress concentration in cylindrical members with the holes. See here, it is a poor design. So poor design is a good design and it is a preferred design. Okay, see. So directly whenever you are doing a threaded portion, so directly applying at this point of view, right? So this. So whenever you are making a neck like this, it is a good thing. So whenever you are using in this manner the diameter over the thread, but here see here, it is along the surface. Next, completely reversed or circular discs, cyclic stresses. Consider a rotating beam of cross section and carrying a load W as shown in the figure. See here, consider a rotating beam, circular cross section rotating and carrying a load of W. This load induces stress in the beam, okay, which are cyclic in nature. Therefore, at a point A, at a point A, at a point A, a little consideration shows that upper fibers of the beam are under compressive stress and lower fibers are under tensile stress. After half a revolution, a point B occupies the position of point A and point A occupies the position of point B. Thus, point B is now under compressive stress and the point A is under tensile stress. Okay, the point A is under tensile stress. Initially, it is now is under pressure. The speed of variation of the stress depends upon the speed of the beam. See here. So this becomes B, this becomes A. Okay, so just here changes in the direction. From the above, we can see that each revolution of the beam, the stress was reversed from the compressive to tensile. The stresses which carry from one value of compressive to the second value tensile or vice versa is completely reversed or cyclic process. Okay, so this type of things, okay, the stresses which vary from minimum to maximum is called as fluctuating stresses. The stresses which vary from 0 to certain value are known as repeated stresses. Okay, the stresses which vary from the maximum value to the minimum value to the opposite nature is called as alternating stresses, right? Next, fatigue and endurance limit. It has been found experimentally that when a material is subjected to repeated stresses, it fails a stress below the yield point stress. Such type of failure of the material is known as fatigue. The failure caused by the means of progressive crack formation, which are usually fine and microscopic size, the failure may occur even without any prior indication. The fatigue of material is affected by the size of the component, relative magnitude of the static and fluctuating loads, and the number of load reversals, right? Next. So if you see the specimens of different time stress diagrams, So you can see this type of various types of standard specimens, completely reversed specimens. So see here, 1 second. Yeah, the radius is this one. So for this, the completely reversed stress. So you are having a even type of stresses. Whereas coming to the endurance or fatigue limit, you are having this type of stress versus number of cycles. Okay, number of cycles in this direction, stresses in this direction. Next, repeated stress. The stress, repeated stress, fluctuating stress, the compression, and the tension. Okay, next. So based upon this fatigue and endurance limit, based upon these relations, we are having the following relations from the figure. That is the mean, the mean or average stress is equals to sigma m is equals to sigma max plus sigma minimum by 2. The reverse stress component is equals to sigma v is equals to sigma max minus sigma minimum divided by 2. Then for repeated loading of each cycle as shown in the figure 2D, this one, to repeated stress flowing in a different ways. Okay, so formula is sigma m is equals to sigma v, that is equal to sigma max by 2. Then the stress ratio R is equals to sigma max by sigma minimum. For a complete reverse stress, R minus 1, and for repeated stress, the R value is 0. Then the R cannot be greater than the 1. Next, the relation between the endurance limit and stress ratio may be given as sigma dash E is equals to 3 sigma E divided by 2 minus R. Next, effect of loading on endurance limit. The endurance limit sigma E of the material is determined by rotating beam method. Which method? Rotating beam method. Okay, thus the endurance limit will also be different for different types of loading. So let us see the modified discussion. KB is a load correction factor. KA is a load correction factor for reversed axial load. It is for reversed rotating or bending load. KS is equals to load factor for reversal shear load. So taking 0.55 for ductile materials and 0.8 for brittle materials, the endurance limit for axial load, the endurance limit for reversal torsional load is equals to so values. Next, so if you see the surface finish and endurance limit based upon the surface finish factor, the various values of surface finish factor for various surface conditions are given ultimate and the tensile stresses. So under salt water, under ordinary water, with mill scale, with a sharp circular notch, machined, polished, mirror polished. So the mirror polish, see here, it is in the straight line, right? So the ultimate strength versus surface finish factor. So under salt water, under ordinary, under with mill scale, like this. So the variations are changing. Coming to the polished and machined mirror polished, it is straight fashion. Next, when the surface factor is known, the endurance limit of the material of the machine member may be obtained by multiplying the endurance limit and the surface finish factor. Therefore, let Ks is equal to surface finish factor. The endurance limit sigma E1 is equal to sigma EB A surface roughness is equal to sigma E into A surface roughness. Okay, now effect of size of endurance limit, the size factor. For the size factor KSZ, endurance limit is equal to sigma E2 is equal to sigma E1 into ASS. For reversed axial load, this is the thing. For reversed shear load, this is a formula. Next, for the miscellaneous factors on endurance limit, A surface roughness and A size factor. For the various temperature factor, reliability factor, and impact factor, the various expressions are for reversed bending load, endurance limit, sigma E is equals to this one. For reversed axial load, endurance limit is equals to this one. For reversal torsional or shear load, sigma E dash is equals to this one, right? So in solving the problems, the value of any above factors is not known. It may be taken as 1. So whenever you are doing the endurance limit problems, so if the value is not known, we can take the value as 1, right? Next, the relation between endurance limit and the ultimate tensile strength. Okay, so the relation between the endurance limit sigma E subjected to the fatigue load for the tensile strength. For a steel, the sigma E is equals to 0.5 sigma U. For a cast iron, is a value, right? Uh, 16, 16, right? For a cast iron, the value. For metals and alloys, this is a value. FO is for factor, fatigue loading. When a component is subjected to fatigue loading, the endurance limit is the criteria for the failure. Therefore, the factor of safety should be based upon the endurance limit. Therefore, FOF is equal to endurance stress limit stress divided by design or working stress. This is the formula. So for a steel, the value of endurance limit sigma E is equals to 0.8 to 0.9 sigma Y. Yield point stress and the endurance limit stress. Fatigue stress concentration factor. Fatigue stress concentration factor. So here the endurance limit fatigue stress concentration factor KF is equals to endurance limit without stress concentration divided by endurance limit with stress concentration. Next one is notch sensitivity. In a cyclic loading concept, the effect of notch or a fillet is usually less than the predicted by use of theoretical factors as discussed. The difference depends upon the stress gradient in the region of the stress concentration, the hardness of the material. The term notch sensitivity is applied to this behavior. It is defined as the degree to which the theoretical effect of stress concentration is actually reached. The stress gradient depends upon mainly on the radius of the notch, hole, or a fillet, or on a grain size of the material. Since the extensive data for estimating the notch sensitivity factor Q is not available. Okay, so these are the various relations, that is stress concentration. Q is equal to Kf minus 1 by Kt minus 1. Right? For shear stress, Kfs is equal to 1 plus Q, K Ts minus 1. So where Kt is equal to theoretical stress factor, Kts is equal to theoretical stress concentration. Now, based upon all this data, we'll solve some of the problems. Problem 1. Determine the thickness of 120 mm wide uniform plate for a safe continuous operation. If the plate is subjected to tensile load that has a maximum value of 250 kilonewtons and a minimum value of 100 kilonewtons. The properties of the plate materials are endurance limit stress is equals to 225 MPa, yield point stress is equal to 300 MPa, the FOS is equals to 1.5. Then write the given data. Let T is equals to thickness to be 5. Area is equals to B into T, that is 120 T. Therefore, average load Wm is equals to W max plus W minimum by 2. So what is the maximum? 250. Minimum is 100 divided by 2, that is this one. Then the mean stress is equals to sigma m Wm by A is the value. And the variable load Wp is equals to max minus minimum by 2, that is 250 minus 100 by 2, that is 75 kilonewton. Then the variable stress is equals to Wv by A, that is this one. So this is the mean stress, this is the variable stress. Then by using the Soderberg formula, this is the Soderberg formula. According to the Soderberg formula, 1 by Fs is equals to sigma m divided by sigma y plus sigma y divided by sigma e. That is equal to 1 by 1.5. So so on so value, applying the values. So in order to find t, we are using this sort of a formula. Keep on changing the values, getting the values. T is equals to 7.64 into 1.5, that is equal to so got it. This is the thickness of the plate. Next problem, the problem 2. Determine the diameter of the circular rod made up of ductile material with a fatigue strength sigma E is equals to 255 MPa, tensile yield strength 350 MPa. The member is subjected to varying axial load. W minimum is equals to so and so value. The maximum is equal to so and so value. Therefore, D is equal to diameter of the circular rod in mm. Area is equals to pi by 4 d square. Next, the mean average load Wm is equals to W max plus W minimum by 2. Okay. Next, the mean stress is equals to sigma m. So this is a value. Then the variable load Wv is equals to max minus minimum by 2. That is so and so value. Next, the variable stress sigma b is equals to Wv by a. So substituting these values, we are getting 636.5 into 10 to the power of 3 divided by d square. So by using Soderberg's formula, 1 by fs is equal to sigma m by sigma y, that is plus sigma b by kf by sigma e. So after substituting the values carefully, after solving this one, we are getting the diameter is equals to 100.5 mm. Next problem. A circular bar of 500 mm length is supported freely at two ends. It is acted upon by the central concentrated cyclic load having a minimum value of 200 kilonewtons and a maximum value of 50 kilonewtons. Determine the diameter of the bar by taking the FOS 1.5, effect is equal to 0.85, surface finish factor is equal to 0.9. Right? So what is the length is given of the pipe? Circular bar is 500 mm. Load is equal to 20 kilonewtons. Maximum is 50 kilonewtons. Factor of safety 1.5. A size factor is equal to 0.85. Surface roughness is equal to 0.9. Ultimate strength is equal to 650. So like this. So we have to find diameter of the bar. So with the maximum bending moment, Mx is equals to W max into L by 4. So this is a value. Next, the minimum bending moment M is equals to W into L by 4. Applying the value, so you are getting the value. Then the average bending moment is equals to M max plus M minimum by 2. So this is the value. Okay. Next, the variable bending moment MB is equals to M max minus M minimum by 2. So this is the value. Next, the section modulus of the bar Z is equals to pi by 32 into d cube, that is equal to this one. Then average bending stress sigma m is equals to m by z, that is 4375 divided by 0.09. So the value is this one. And then the average variable bending stress sigma b is equals to mb by z. So applying the values, you are getting this one. Then by using the Goodman's formula, 1 by f is equals to fs is equals to sigma m by sigma u plus sigma b into kf by sigma e into a surface roughness into surface size. 1 by 1.5. So applying the value sigma m by sigma u plus also values. Taking factor kf is equal to 1. So after substituting all these values, d cube is equals to so also finally d is equals to this one. Then by according to the Soderberg formula, 1 by fs is equals to 1 by fs is equals to sigma m by sigma y. Right? Then again by using the diameter d, d is equals to dq is equals to so and so value. So therefore d is equals to 62.1. So with these two values, which is the largest one, so we have to take the largest one value is 62.1 mm diameter. Got it? Next problem. 4. A 50 diameter shaft is made up of carbon steel having ultimate strength and subject to torque with the fluctuates using the Soderberg method calculated FOS. So diameter is D is given 50, strength is given 630, T max is given 2000, T minimum is given minus 800. Therefore, this one is equals to T max plus T minimum by 2. Applying this one, you are getting the value. So the average shear stress T max is equals to this one. Variable torque TV is equals to, after simplifying the values, you are getting the value this one. Therefore, the variable shear stress tau V is equals to sigma dV 16 dV by 5 d cube. So this is the value, right? So by applying the endurance limit reversal bending factor, tau E is equals to 0.5 by Eg sigma E. So by substituting values, you are getting the value. And by assuming these values, tau I is equals to sigma 0.5 into sigma Y. Therefore, 0.5 into 5 times, that is the value is this one. Therefore, factor of safety, we know that Fs is equal to factor of safety by using the Soderberg formula. The Soderberg formula, applying the values in here. So after solving this one, we will get the value of factor of safety is 1.85. Okay. Next problem. Next problem. A simply supported beam, the concentrated load having the values, the span of beam is 500 mm, the diameter is 60 mm, the stress is 700 MPa, yield stress is 500, endurance limit is 330, factor of safety is 1.3, the size factor is 0.85. At the given values, okay, D value, sigma E value, Fs, Fks, F surface. So by applying the bending moment, M max is equal to W max into L by 4. So this is a value. And the minimum bending moment, M minimum is equals to W minimum into L by 4. That is a value. The mean average bending moment, MM is equals to M max plus M minimum by 2. Substituting again in the formula. Therefore, the variable bending moment MB is equal to M max minus M minimum divided by 2. This is a value. Then the section modulus Z is equals to 5 by 32 d cube. There is a value. Then the mean bending stress is equals to this one. Then the variable bending stress sigma V is equals to MV by Z, that is equals to 0.0088p. And by using according to Boltzmann's formula, substituting values in all the ways. So we have got P is equals to 1 by 1 by 3 10 to the power of 6 by 55.8. The value is this one. Okay. And by using Soderberg formula, 1 by Fs is equals to sigma m plus sigma y. So now substituting values for the above equation. So we are finding the maximum value of P is equals to 11.982. So by making these two values, so which one is the maximum? 13.5 is 13.7, that is 14 is maximum. Therefore, the pressure P is equals to 14 kilonewtons. So with this, we have completed the unit 2 successfully. So in the unit 2, majorly we don't have any theoretical concepts, only the definitions like what's the meaning of knot sensitivity, what's the meaning of endurance limit, what is the fatigue factor. Other things we are having the problems related to the stress concentration factor by using Soderberg's and Goodman's formula, right? So practice these problems for your exam point of view. So unit 2 mainly discuss about a few concepts, that is endurance limit, knot sensitivity, okay, the stress concentration factor, and the problems associated with the Soderberg's and Goodwin's formula, right? So if you practice these problems, you will get similar type of problems in the exam point of view. The method of doing is by using Soderbergh's formula on the maximum bending moment, minimum bending moment, variable bending moment, and modulus of the bar. Okay, so you have to apply the Soderbergh formula or a Goodman's formula based upon the input data given, and we also solve the problems. Got it? So practice the problems whatever given in this video. Okay, so whatever the concepts we have designed, discussed in the unit 2, we have completely discussed the concept design of fluctuating stresses, endurance limit, estimation of endurance strength, problems related to Goodman's line, Soderbergh's line, and the modified Goodman, Goodman's line, right? So the major thing is related to the stress concentration concepts. So the theoretical concepts like what's the meaning of defined non-sensitivity, or what is the um, fatigue, what is the stress concentration, what are the fluctuating stresses. So these are the types of theoretical concepts which comes in the unit 2. Okay, so with this we'll wind up the class. So we'll discuss in the other concept, right? So thanks for watching the video. Have a good day. Okay, so with this I can wind up the session. So with this session, the total DMM subject has been revised for all the units, unit 1 to unit 6, by taking 14 lectures, 14 revision classes. We have wound up the DMM1 subject for mechanical second year, second semester students. Got it? Right.